Welcome to this video, where we explore the context and proposition behind John Norton's dome, a fascinating thought experiment that challenges our understanding of determinism. This thought experiment seems to break the rules of classical physics, suggesting that a ball can start moving for absolutely no reason. But is it a genuine threat to Newtonian determinism, or just a clever trick of the math? Let's find out. The core insight of our argument is straightforward. Norton's dome appears to be a paradox, a thought experiment that undermines Newton's clockwork universe. However, we propose it's not a discovery about nature. Instead, it's a powerful demonstration of the limits of the mathematical tools we use to describe nature. When we apply Newton's physics to real-world conditions, it remains deterministic. Next, let's look at the specific claims made regarding this paradox and what was said in the academic discourse surrounding it. So what is Norton's claim? It rests on a specific mathematical premise. First, he shows that the dome's equations of motion have multiple solutions, one where the mass stays at rest forever, and others where it spontaneously slides at any arbitrary time. Second, he argues that because the same initial conditions yield multiple valid trajectories, Newtonian mechanics is formally indeterministic. And third, the philosophical consequence. This challenges the idea that every event must have a cause, a blow to Laplacian determinism. Now, we will address the problems and the fundamental weaknesses identified in this argument. But here's where the paradox hits its limits. While mathematically valid, the physical model fails. On the left, you see the problem of unphysical geometry. The dome requires a singular curvature at its very apex, violating smoothness conditions that are needed to guarantee unique solutions. No real material could be shaped this way. On the right, we see the limits of calculus. The paradox arises from the infinite divisibility of time. In continuous time, there is no first instant of motion, which is a property of the math, not of physics. The physical universe, however, resolves this. On the left, discrete time. Modern physics suggests time may be quantized at the Planck scale. In a discrete model, there is a first instant after time t, immediately restoring determinism. On the right, we have physical noise. Real systems experience friction, Brownian motion, and quantum fluctuations. These break the perfect, ideal symmetry Norton relies on, ensuring that any motion has a physical cause. His brings us to the fundamental category error of the paradox. Norton conflates the determinism of a formal mathematical system, the equations on paper, with the determinism of the physical universe itself. It's a map versus territory problem. The dome paradox successfully exposes the limits of a mathematical model, but it tells us nothing about the fundamental laws of nature. Let's analyze the logic behind this divide and how we can bridge it. So how do we move forward? A systems theory framing bridges the scholarly divide between mathematicians and physicists. The paradox is what we call a boundary error of calculus. By clearly distinguishing the mathematical formalism, the map, from physical reality, the territory, we see that the dome demonstrates the limits of continuous mathematics, not a breakdown of determinism in the real world. This view is supported by a scholarly consensus that isolates the paradox to the realm of mathematical formalism. Let's look at the table. Norton's claim that Newtonian equations admit indeterministic solutions is true mathematically, but physically irrelevant due to unphysical geometry. This is supported by Weatherall, who showed the dome violates system constraints. When he claims the dome challenges determinism, we argue it challenges calculus, a distinction backed by Ehrman. And finally, the issue of no first instant is resolved by discrete time, supported by theories of quantum gravity. Finally, let's summarize the implications of this analysis. Norton's dome is a clever mathematical construct, but it does not undermine Newtonian determinism in the physical world. The paradox produces, quote, ghost solutions derived exclusively from infinite divisibility and singular geometries. When grounded in physical reality, these anomalies vanish. Newton's physics remains deterministic wherever it is physically applicable. The final takeaway is simple. Models are tools, not truths. When a model predicts spontaneous, uncaused motion, it reveals the limits of the tool, not the laws of nature. The map must always be checked against the territory. The critique above stands on its own. What follows is not part of the argument itself, but an addendum for readers who want to understand the broader conceptual landscape. We will explore various fallacies, essentially breaks in logic, and how they manifest when abstract mathematics is applied to physical systems. We introduced John Norton's dome paradox and argued that it's a mathematical construct, not a physical threat to Newtonian determinism. Now, we're going to go deeper. We'll systematically dismantle the paradox by identifying the specific logical fallacies and category errors at its core. Let's get into the critique. Our critique begins with two fundamental fallacies. The first is an equivocation on Newtonian. Norton uses the same term, Newtonian, to mean two very different things: the formal mathematical framework of differential equations on one hand, and the physical theory applied to real-world objects on the other. This conflates the map with the territory. A formal differential equation like F equals ma is not the physical law itself. It's a description that comes with implicit constraints. The second is an appeal to mathematical possibility. Norton treats a formal mathematical solution as sufficient proof of physical possibility. Just because the equations admit a solution doesn't mean the universe must allow it. Mathematics permits artifacts like singularities and infinities that physics explicitly forbids. Possibility in formalism is not justification in physicalism. Fallacy number 3 is ignoring domain validity. This is the technical heart of the problem. Norton constructs a dome that deliberately violates a mathematical condition known as Lipschitz continuity. This condition is the very guarantee that a differential equation will have a unique, deterministic solution. By feeding the model an invalid input, a non-Lipschitz geometry, Norton manufactures the paradox. It's like asking a calculator to divide by 0 and then declaring that mathematics is broken. Physics is not required to answer questions posed outside its domain of applicability. Moving on to fallacies 5 and 6. Number 5 is the category mistake of attributing properties of a mathematical continuum, like infinite divisibility, to physical time. Norton relies on the real number line to argue there is no first instant in an open interval. But if physical time is discrete at the Planck scale, that argument evaporates completely. Number 6 is a false equivalence. Norton equates a mathematical function, an arbitrary description of motion on paper, with a physical object's actual behavior. The function x of t describes the motion, but it provides no physical mechanism for initiating it. A physical event requires causal efficacy, energy gradients, perturbations, or forces. The math is a description. It is not the event itself. Fallacy 7 is explanatory inflation. Norton takes a single, exotic mathematical anomaly, a non-Lipschitz geometry, and inflates it into a global crisis for classical physics. This ignores the fact that 99.9% of all Newtonian systems, and all physically realizable ones, remain perfectly deterministic. Finally, number 8 is an ad hoc idealization. The paradox relies entirely on a physically unattainable premise, a mathematically exact, infinitely smooth, frictionless dome with a perfect point mass. This is an impossible idealization. The instant you add friction, thermal noise, or quantum fluctuations, the spontaneous motion is replaced by predictable, causally driven perturbations. The paradox collapses. To summarize the critique, let's look at this table. It maps each of Norton's moves against the flaw it commits. The formal equation F equals ma fails to account for physical constraints. Mathematical possibility ignores that physics forbids certain artifacts. The non-Lipschitz input violates domain validity. Pure mathematical abstraction ignores physical constructibility. The mathematical continuum ignores discrete physical time. The arbitrary function lacks a physical causal mechanism. A boundary singularity is inflated to claim universal indeterminism. And the perfect idealization collapses under friction and thermal noise. This is what we call the epistemic tax. Norton is forcing physical reality to pay for the limitations of his mathematical model. But the universe doesn't owe us an answer to a badly posed question. Next, we will look at key concepts and the essential terminology needed to understand these logical breaks. The balanced pencil illustrates our first core concept, Lipschitz continuity. In the mathematical formalism, the pencil can fall in any direction, multiple solutions, no unique outcome. This is exactly what happens when a system violates Lipschitz continuity. But in physical reality, the pencil never falls for no reason. A quantum fluctuation, a tiny air current, a vibration. These perturbations break the perfect symmetry and produce a unique, causally determined trajectory. Norton's dome is engineered to be the mathematical version of the balanced pencil. It exploits the failure of Lipschitz continuity to produce multiple solutions. But just like the pencil, the physical dome would always have a perturbation that selects a unique path. The math allows indeterminism. The physics enforces determinism. Our second core concept is the distinction between map and territory, illustrated here by the border schematic. On the map, The border between two countries is an infinitely thin line. It has no width, no physical properties, but in physical reality, that border has measurable width. There's thermal noise, material imperfections, discrete time intervals, real physical features that the abstract map ignores. Norton's paradox exists exclusively on that infinitely thin line of the mathematical model. It's an artifact of the map's abstraction. When we check the territory, when we examine the actual physical conditions, the paradox vanishes. Thermal noise, material imperfections, and discrete time restore determinism. The dome is a classic case of pushing a model beyond its valid domain. The map is not the territory. Let's revisit the core concept of determinism. We must clearly distinguish between formal determinism and physical determinism. In the formal system, the differential equations admit non-unique outputs for singular inputs. This is where the math breaks down, much like a calculator displaying an error when you try to divide by zero. The failure is in the tool, not in the universe. The actual physical behavior, however, remains perfectly deterministic when applied to well-posed physical systems. The formal failure of the math does not imply a physical failure of the universe. The tool has reached its limit, and that's all. So what is the ultimate conclusion? The dome paradox is a modeling breakdown. Our mathematics, specifically the calculus of continuous functions, breaks down at boundary case singularities. The paradox is a boundary error of a calculus-based model, not a revelation about the physical cosmos. When we check our model against the territory of physical reality, we find that the anomalies vanish. The universe, wherever it is physically applicable, remains deterministic. Norton's dome is a brilliant demonstration of the limits of our tools, but it tells us nothing about the fundamental nature of cause and effect.